Hi, this is the video on chapter 25 on two sample inference procedures with means, aka matched pairs. So let's get started. So we're first going to start with four different instances where I'm going to ask you the following. Decide which should be analyzed using one sample matched pair procedure or which should be analyzed using two sample procedures. So this is really dependent on whether or not you read chapter 25 and being able to answer the question. So here's the situation. A pharmaceutical company wants to test its new weight loss drug. Before giving the drug to the random sample, company researchers take a weight measurement on each person. After a month of using the drug, each person's weight is measured again. So again, is this a one sample matched pair procedure? Or is it analyzed using a two sample procedure? And the verdict is matched pair. The reason why, again, the reason why, according to that, is that you're taking the weight of the same person at different times. So since it's the same person giving that, that's where before and after, that's the matched pair. All right, so let's take another look at a different example. So again, same situation, tell me whether the situation is using a one sample matched pair procedure or analyzing using two sampled procedure. So here's this situation. A researcher wants to know if a population of brown rats on one city has a greater mean length than the population of another city. She randomly selects rats from each city and measures the lengths of their tails. So which do you think? Is it one sampled matched pair or is it two sample procedures? And the verdict is two independent samples. It is a two sampled procedure. Again, the cities are different. They're independent of one another. So the information of rats from one city is definitely different from the other. All right, third example. All of the following situations, decide which should be analyzed using one sampled matched pair procedure and which should be analyzed using two sampled procedure. And the verdict, or excuse me, the situation is a researcher wants to know if a new vitamin supplement will make the tails of brown rats grow longer. She takes 50 rats and divides them into 25 pairs matched by gender and age. Within each pair, she randomly selects one rat to receive the new vitamin. After 6 months, she measures the length of the rat's tail. So, verdict is matched pair. But please be careful. It says the word match. Just because it says the word match, that's not the reason. The reason why, again, look at what's happening with the rat. They're receiving the vitamin and then checking the same rat's measurements again. That's why it's matched. All right, last one. A college wants to see if there's a difference in time it took last year's class to find a job after graduation and the time it took the class from 5 years ago to find work after graduation. Researchers take a random sample from both classes and measure the number of days between graduation and first day of employment. So what do you think? And the verdict is two independent samples. It's a two sampled procedure. So think about why. Hopefully you see it. You have the class that's 5 years ago and you have the class that's right now. They're definitely different, independent from one another. Definitely not a sampled matched pair, a one sampled matched pair. All right, so let's talk about matched pairs. Matched pairs are a special type of one sample means. In fact, we're going to be using a t-test and a t-interval. for matched pairs. I'll say that again. That's a one t-test, one sample. Even though we have two sets of data, we are going to only use a one sample means. We'll show you how in just a moment. So let's first go through our conditions. They have slightly changed when you have a matched pair. The very first thing is that you have to have samples that are paired. The sample differences can be viewed as a random sample from a population of differences. So again, the sample differences can be viewed as a random sample from a population of differences, but they have to be paired. All right, second thing, the sample distribution of differences is approximately normal. So we must look to see if there are any outliers. We must look to see what that looks like. And again, there are several things to look like for approximately normal. The first thing to look for is sometimes it's given in the problem that it's known to be normal. So it'll say it in the problem. Or the number of samples different is large. So you may have the sample difference to be n is greater than or equal to 30, and that would mean that it's approximately normal. Or you take a look at the graph, usually a histogram. You do need to look at your box plot and look to see what that shows. If your histogram shows that it's unimodal and symmetric, then we can say that it's approximately normal. Thirdly, you have your 10% rule. The sample of differences is not more than 10% of the population of differences. Okay, so your CI, your confidence interval, is equal to your statistic plus or minus your critical value times your standard deviation of your statistic. So what is that? This formula should not be new to you. You've been seeing this, I don't know, for quite a long time. So what is your statistic? X bar. Again, we're dealing with means. There's my X bar. But we subscript it with a D. The critical value, since again, we're dealing with means, it's a T star. Don't forget your degrees of freedom there. Multiplied by your standard deviation of the statistic. So you have your S, sub D, divided by the square root of n. And again, don't forget your degrees of freedom is still n minus 1. All right, so that is dealing with your formula. Don't forget about your parameter. Your parameter is mu. And again, since all of these have been d's, we do mu sub d, which is the true mean difference in and whatever the information is about. Your hypothesis statements is mu sub d is equal to whatever your hypothesized value is. Now, again, this is a single t-test, a single t-interval. The value here is whatever the value that you're given in your problem that you're testing against. All right, so, and remember, we still have our 3 different versions of what we could have as answers for your alternative hypothesis. All right, I'm going to pause here and end our video and come back in just a moment.